Swayam Prabha. Digital India. Educated India.
Okay, in the last lecture we had looked at some of the important principles that have to be considered while designing a new product, and today we are going to talk about product mix. That means no company would ever be talking about marketing only a single product. It would be marketing a number of products together. And therefore, this question of finding out how many units of which product should be marketed, this is an important question. So, this is what we refer to as the product mix problem in the context of designing and introducing new products. I think a question that normally comes to mind is that if there are a number of products and if that one particular product is the most profitable, then why not keep on producing quantities of that particular product and ignore the products which are less profitable. So, this is the reason for this observation, that it may seem that choosing the most profitable product in large quantities would maximize profits. However, in practice this need not be so. Why? There are a number of reasons as to why this will not happen in practice. First of all, there would be a large number of constraints which would have to be considered before introducing any new product. Typical constraints could be, for instance, demand constraints. When we talk about demand constraints, what we are talking about is that the quantities to be sold of individual products could be limited by the market demand for those products, and therefore it is not entirely in your hands to be able to sell as much of the product as you want, even if the product is most profitable. So, these are very significant constraints which have to be considered. Commitment to produce multiple products might be made by the company. It might have already committed to a large number of customers that it would supply some products. Some of the products may even be becoming obsolete, but for the sake of goodwill of the customer, you are committed to producing those products, and therefore you would have to produce multiple products in the whole mix of products that you make. To absorb the risk of producing only one product. You have all heard of that phrase, don't put all your eggs in one basket. So, most companies are risk averse, and they would like to make sure that they don't put all their eggs in one basket. So, if this is so, this means that the option they have at their disposal is to produce in a large number of products, and so that the risk can be shared by those products. Another common reason for introducing variety as far as product mix is concerned is to expand the customer base. So, what happens typically is that one product captures a certain fraction of the market. If you introduce another product that product will probably capture another segment or an overlapping segment of the market. So, if you have a large number of products, you probably cater to a large number of customers. What is the reason that a company like Coca-Cola, for instance, makes not only Coca-Cola, but also a number of Fanta and various kinds of drinks which are there? The reason is only to capture a greater customer base and introduce product variety as a consequence. Another reason for the introduction of products in the market, new products, is utilization of resources. Quite often, with one product you might not be able to utilize all the existing resources that you have, and therefore you might want to introduce some related products so that your resources are better utilized in that sense. So, this could also be a consideration. So, it becomes therefore almost imperative for a company to introduce variety, introduce a large number of products together and talk about developing a product mix. So, that is the problem that we are addressing ourselves to today, how to determine the optimal product mix for a company, and we are going to examine a number of different situations and a number of mathematical models which can be used for answering this particular question. Let us first take an example of a situation with which we are already familiar, and the problem is that suppose a company is producing 3 products, we call them A, B and C. These 3 products require processing in 3 different departments. These different departments could be, it could be a lathe, it could be a grinding machine, it could be a milling machine, or in general we are talking about 3 different departments. And apart from these 3 different departments, the product requires to be inspected. So, there is an inspection department and then there is a shipping department. So, there are these 5 departments which come into play in the manufacture of these 3 different products. The information that we have at our disposal is processing time in hours per unit. So, we have estimated, for instance, that if a unit of product A is to be estimated, it would require 0.14 hours per unit in department 1. Similarly, it would require 0.6 hours per unit in department 2 and so on in different departments. And notice of course that product C does not require any processing in department 1. And the unit profit from sales of these 3 products are given here: 42 rupees, 40 rupees, 36 rupees is the profit that you earn by selling 1 unit of product A, B and C respectively. And it is given that the sales for these products vary, and historical experience shows that the minimum sales for this product is 150 units for the planning period which we are considering, and it can at most go up to 250 pieces per period. Similarly, the figures for product B are 200 minimum sales and 400 maximum sales for the product B, and for product C the corresponding figures are 360 and 500. So, this would be typically the kind of data that you would require for doing any product mix problem using, let us say, linear programming. We are talking about the case when we can handle this through linear programming. Obviously, the assumption that we are making is that costs vary linearly, which means that if it takes 0.10 units hours per unit to make one product, 2 products take 0.20, 3 products take 0.30 and so on. So, that is the assumption we are making. In effect, what we are ignoring here is the fixed costs, or you may assume that the fixed costs are actually included in these and we are making the assumption that costs are linear. So, in this data that we have collected for these 3 products, we have the processing time in hours per unit, and then we have for each of the departments the hours of capacity. For instance, department 1 has a capacity of 160 hours, department 2 has a capacity of 320 hours, department 3 has a capacity of 160 hours, and similarly the inspection and shipping each have 80 hours. So the differences in the capacities, as I mentioned, could be because of the varying number of shifts that you operate these various departments in. Now let's try to formulate a linear programming problem for this particular example. Our decision variables are clearly x1, x2 and x3, the quantities of A, B and C to be produced. And since the profits are 42 rupees, 40 rupees and 36 rupees respectively from a unit of sales of each of these products, then we can easily write down the expression for the objective function, which is to maximize the profit, which will be 42x1 plus 40x2 plus 36x3. So this is what is to be maximized, subject to the various constraints. Now the constraints in this problem are essentially the capacities of the various departments. For instance, the first department, if you see, has a capacity of 160 hours and it processes product 1 and 2 and does not process department 3. So if you look at the column in that particular data that we were examining a short while ago, you will find that 0.14 hours per unit is the requirement of producing a unit on unit of A, and 0.10 is the requirement of producing a unit B as far as the first department is concerned. So the total time required for the production of these items is 0.14x1 plus 0.10x2, and this should be less than or equal to 160, which is the number of hours available. We would have a similar constraint for each of the departments. We have 5 departments, so 1, 2, 3, 4, 5. The right hand side here is the hours of availability, and this is the total consumption in terms of time in the various departments, depending upon the processing times and the quantities to be produced. And then we have sales restrictions. The typical sales restrictions for this problem are that x1, that is the quantity demand for the first product, should lie between 150 and 250. So we have a constraint saying that x1 is greater than or equal to 150 and less than or equal to 250. And we would have similar constraints for the other 2 products. Product 2, for instance, has a sales which will lie between 200 and 400. So we say x2 should be greater than or equal to 200 and less than or equal to 400 as shown here. And similarly, the third product you have should be, the demand lies between 360 units and 500 units. So what we are basically interested in is developing these constraints. So we have the total number of constraints for this problem is going to be, we have 5 of these constraints, 1 for each department. Then for each of these 3 products we have an upper bound and a lower bound constraint. So 6 such constraints. So the total number of constraints that we have is 11, and we have 3 variables, 3 decision variables, x1, x2, x3. Now the solution to such a problem can easily be obtained by using any one of the computer packages which are available. You may use, for instance, Lindo or Micromanager, which is available in the industrial engineering laboratory. And we will therefore not go into the solution techniques, because you are already aware of the ways of solving linear programming problems. So if we look at the solution from a package, we find the following. We find that the total profit is 28,016 rupees, and the values of x1, x2 and x3, the optimal values of x1, x2 and x3 work out to 168, 200 and 360 units respectively. Now apart from this information about the product mix, so this is the optimal product mix and this is the profit that you get from this particular product mix. There is some useful information that you get from the output of a typical LP package, and I am just pointing out here some things that need to be emphasized. For instance, in the optimal solution, it is found that only 3 constraints are satisfied as equalities, and these are the 3 constraints which are satisfied as strict equalities. The other constraints, that means out of the 11 constraints, only 3 constraints are satisfied as strict equalities. That means the left hand side is exactly equal to the right hand side, and so on. This particular constraint, as you can see, is nothing but the utilization of a particular department. You can see, for instance, that this pertains to, let us check up from the data as to which department it refers to. You would see, for instance, that if you look at the problem, we are referring to the shipping department here. So this is a constraint corresponding to the shipping department, which says 0.10x1 plus 0.10x2 plus 0.12x3 should be less than or equal to 80, which is the capacity of the shipping department in that sense. Since this constraint is satisfied as an equality, and similarly we have x2 is equal to 200 and x3 is equal to 300. For all such constraints which are satisfied as strict equalities, you can calculate a shadow price or a dual variable, and these shadow prices or dual variables are available in the solution that you obtain from any package. The interesting thing about the dual variable really is that here, corresponding to this constraint which pertains to shipping, the entire 80 hours of shipping are currently being utilized, and the shadow price for this particular constraint is 420. What it shows is that if you increase the capacity of the shipping section by 1 unit, that is, make it from 80 to 81, the contribution to the profit is likely to be 420. So the dual variable or the shadow price gives you very valuable information as to which particular capacities to increase and which not to touch. The other capacities which are all equalities at the which are all inequalities at the moment, they would not contribute to the objective function. For instance, this is being utilized fully, so increase in 1 unit will do. Now take this particular constraint. The constraint says that this is a greater than equal to constraint which is 200. It's a negative value. The significance is that if I reduce this by 1 unit, the profit will go down by 2 units. That means if the market demand, this is the market demand, currently you are selling 200 units. So if the market demand falls by 1 unit, your profit will fall by 2 units. That's the implication. Similarly, this one is greater than 360 units. So if this falls by 1 unit, the profit is likely to fall by 14.4 units. So linear programming is a very worthwhile tool which can not only determine the optimal product mix and the corresponding maximum profit, but it can also give you very useful hints on how to improve your profits and where to invest for improving the profits. So I think this is another point about linear programming which needs to be carefully understood and applied when you are dealing with real life problems. After having looked at the simple linear programming problem, in real life there can be a number of conflicting multiple objectives. So let us say that the same company which is dealing with the same 3 products has these 3 or 4 considerations or goals to consider. The first goal in the order of priority is ensure that a profit of at least 80% of the maximum profit is realized. 2, that you want to maximize the utilization of department 1. Department 1 has 160 hours of capacity. In the current optimal solution, the department 1 is underutilized. So they want to maximize the utilization of department 1 at a second priority. Third thing is ensure at least 20 hours of idle capacity in department 2. What could be the motivation for an objective like this? It may so happen that the company is interested in or is already committed certain capacity of this particular department to other users. So it would like to make sure that at least 20 hours of idle capacity are retained in department 2. And the fourth constraint is ensure that the utilization of department 3 is exactly 150 hours. So we are using this example to see how a goal programming formulation could be set up for this case, and I think that would give us some insights into how to handle multiple constraints. The essence of goal programming is the use of deviational variables, and what happens is that what is a deviational variable? A deviational variable is that if you set up a target for something, so this is my target. Now in an actual situation I might overachieve the target or underachieve the target. So we use two kinds of variables called overachievement variables and underachievement variables, denoted by D plus and D minus respectively, which tell you how to achieve the target. For instance, suppose you are aiming for getting marks of 75 in a particular course, and if you overachieve your target, for instance if your score is 90, you have overachieved your target by 15 marks. However, if you get 50, you have underachieved your target by 25 marks. So basically these deviational variables measure whether you have overachieved or underachieved the target. And mind you, in goal programming we are always dealing with targets, unlike linear programming. In linear programming you are always trying to choose a favorable direction and you are trying to maximize or minimize your travel on that particular direction. For instance, you choose profit and you say I want to maximize profit, and when you are maximizing profit in linear programming you are essentially saying that okay, this is the road to profit, I want to go as far as possible without saying how much you want to go on that road. Whereas in goal programming we set up milestones on that road and we say okay, we would like to have a profit of at least 2 million rupees. So we have set up a milestone on that road, and in goal programming we are more concerned about achieving those milestones rather than trying to maximize or minimize, as the case may be. The goal programming objective function then is set up in terms of these deviational variables. So this goal programming objective function is a function of only deviational variables. The objective function is always a minimization function because you are talking in terms of minimizing the deviations from targets, and it is priority wise or hierarchical in nature. That means you choose a set of priorities and work according to that particular set of priorities. So these are some of the basics that are required for understanding a goal programming formulation. In goal programming, which is actually an extended version of an LP formulation, there are two types of constraints. First type of constraints are called goal constraints. There is a goal constraint, one for each goal. So this links the goal to the deviational variables. And then of course there are the system constraints, which are the original constraints that appear in the LP formulation. So we will try to develop for our example both the goal constraints and the system constraints so that we have the complete goal programming formulation. What we have here is the objective function and the goal constraints for the problem. Since we have 4 goals, so we have 4 goal constraints, and the right hand sides here are the target values that we have set. We have set a target of 80% of the Z max. Z max is the value that you obtain through the linear programming problem. And then what you notice is that we have, this is the total profit, this function, minus the underachievement, minus D1 plus D1 minus, that means minus the overachievement plus the underachievement should be equal to the target, and exactly similar considerations apply to the other 4. For instance, here this is the total hours consumed in the first department minus the overachievement plus the underachievement will be equal to 160. So this is the same concept, that you can either overachieve or underachieve, you don't know. That's why we have both the variables. And remember, these variables are such that only one of these variables will be in the basis at an optimal solution, because if you are aiming to achieve 75 marks, you will either get more than 75, in which case D plus will be in effect, or you will get less than 75, in which case D minus would be in effect and the other deviational variable will be 0. So we write down these deviational variables corresponding to the first constraint, the second constraint, the third constraint and the fourth constraint, and we write these, and these are nothing but the goal constraints. That is what we mean by the goal constraints. Now look at the objective function. If your objective function, the P1, P2, P3, P4 refer to the priority levels. The first priority goal is to ensure that you get at least 80% of this profit, isn't it? So what we want to do is that the negative deviation from this should be minimized. We would like to have the negative deviation from this to be 0 ideally, isn't it? So that is why we include this in the objective function. Similarly, the second one, we want to maximize the utilization. Now maximum utilization possible, as you know, is 160 hours, and plus is if you overachieve it, minus is if you underachieve it. So D2 minus is what you want to minimize. So D2 minus is taken in the objective function. Similarly, P3 is we want to, again, this is the utilization of the third department, and what we want to do is we want to minimize this underutilization of this particular department. And what we have done is, you know, the capacity was 320, we have already subtracted 20 units, so that we had our target performance for this particular utilization of department 3 is only 300 hours, after accounting for 20 hours of idle time which we wanted on this particular department. So then you want to minimize D3 minus, so you have this. The fourth priority goal was that we would like that in the fourth department the exact utilization should be 150 hours. So this is a situation where you would like to minimize the sum of both D4 plus and D4 minus. So when you are exactly trying to achieve a goal, this is the mechanism that you adopt for ensure, because when both of these are 0, then this will be minimized, and that would mean exact utilization of 150. So in a nutshell, the goal programming formulation encompasses, as far as the objective function is concerned, 3 types of deviational variables. You could either be minimizing some D minus, or be minimizing some D plus, or be minimizing the sum of both of these. So it all depends upon whether you want to minimize the overachievement or the underachievement, or you want to exactly stick to the goal. So you will have this. So this is our objective function, and then the goal programming problem will be now complete if we add to this the system constraints. The system constraints are the same constraints that we used in linear programming. All those constraints as it is come here. So now the problem is complete. We have a goal programming objective function, we have a set of goal constraints and the system constraints, and we can use this to solve the problem. You can use the package of Lee and Moore for solving this particular problem, and ultimately the solution to this particular goal program is given here. We find that we have found out the product mix, that is 168, 200, 360, and then we have found out the deviational variables. What is the significance of this deviational variables? Let us see. See, our target was 80% of the goal. So having taken that as target, D1 plus says that we have overachieved that target by 563. So the total profit is the original profit goal plus 563, which is this profit 22976. So this is the total profit. Similarly, the utilization for department 1, utilization for department 1 or D2 plus was 0 and D2 minus was, that means we underachieved the utilization of the department, which was 160 by so much. So this much was the unutilized capacity. So utilization was 43.52 only, and so on for utilizations of other two. So you can accommodate multiple goals and find out the values of the objective function and the other utilizations and other goals that you want by treating this kind of thing. So goal programming is basically, as I said, an extension of linear programming in which we could accommodate a variety of goals and solve the problem. Let's look at a third problem in the context of the product mix. Let's look at this problem of what we call the unconstrained stochastic product mix. So far we have assumed that the product demands are deterministic. Now if we assume that the product demands are not deterministic, but they are probabilistic and maybe follow certain probability distributions, how are we going to determine what is the optimal product mix in such a situation? Just to keep the problem simple, we will consider the following assumptions. We will make sure, we will assume here that there are n different items. These n different items have uncertain sales potential. That means we do not know exactly how much each item will be able to sell, and the demand for an item is a random variable with a specified probability density function. That is what we will assume. Okay? And this would be something that would come to you from experience, right? You would know, for instance, that if you have been selling every day say certain medicines, the chemist knows that the demand for crocin is like, daily demand for crocin is likely to be anything from 10 to 400 maybe, depending upon the season, right, whatever it is, and you could probably fit some suitable distribution to that. And we will assume that it is a short duration sale, just to simplify things so that we do not have to consider other types of costs, and there is no opportunity to reorder. Let me give you some examples of this situation. For instance, if it is known to a company, suppose a number of companies are preparing for setting up an exhibition at Pragati Maidan, and this is going to be a short exhibition of, let us say, 3 days or 4 days, and they want to keep different items for sale, and each item has a probability distribution for sales. That is what we are trying to say. So what we are, the question that we are trying to address is, how much of each item should this company stock in the sale such that its expected profit is maximized, right? And the maximization of the expected profit should be subject to the consideration that during this period of the sale, which is a short term sale, we are not allowing fresh consignments to come in. That means whatever they have brought in the beginning, only that. So either they will have sell everything or they will have shortages, as the case may be, but we are not allowing for new replenishments during this period. That is it. Okay? This is the basic idea. In fact, jocularly, this is the problem of the sabzi wala who goes to the mandi every day. Right? Every day in the mandi he has to buy different vegetables. So these are the products. He knows from past history the demand for each of these vegetables. आलू जो है 10 किलो और 15 किलो के बीच बिकता है, and so on. भिंडी इतनी बिकती है. So this assortment of vegetables he has to buy. He has to decide every day how much of vegetable to buy each day, such that this is an ongoing affair. Every day he will have to do this decision, such that his expected profit is being maximized. And once he brings the sabzi to his shop, he will not be able to go to the mandi during the course of the day to bring additional sabzi. So we are basically talking about that situation. So this is the second example. The third example that I can give you is, for instance, take the case of perishable commodities. All perishable commodities like medicines, foodstuffs, they have a shelf life. So a typical supermarket might be interested in finding out the quantities of different items to stock for a certain period, such that their expected profit is maximized, assuming that there are no further replenishments during that period, because the replenishments from a chemist or something generally come only on a particular day, on Mondays, when the supplier comes and gives you the supplies in that sense. So this is the kind of scenario that we are trying to model here. So let's look at this problem. Let's first introduce some notation to formalize the problem. Let's say xi is the initial stock level of item I. So this is our decision variable. We won't need to find out how much of each item to stock. Ci, small ci, is the unit procurement cost of item I. Ri is the unit selling price or the revenue that you get if item I is sold during the sale. And Ri prime, actually what we are talking about here is not Ri but Ri prime. So Ri prime is actually the unit disposal value of item I if not sold during the sale. So what we are saying is, take the example of the vegetable vendor again. If he sells potatoes during the day, he will probably be able to get 10 rupees per kg, but if they stay on till the end, he will have to dispose them off at 2 rupees per kg or 3 rupees per kg. So that is the disposal value, and this is the unit selling price. Capital DI is the demand of item I during the sale, and this is the random variable which we are assuming has a PDF of FIDI. So this is an arbitrary PDF. It could be a normal, exponential, Erlang, any distribution that you want. Okay, so in general FIDI, and Z is the contribution to profit and overhead from the sale. That means our objective function is this Z, but Z is a random variable, so we will talk about the expected value of Z, and that is what we are interested in maximizing for this particular case. Let's try to do a bit of analysis. For a given set of stocks that you have of different items, which is x1, x2 and so on up to xn, and a given realization of demand, which is d1, d2 and so on up to dn, the quantity sold is denoted by S, which is a function of xi and di. Obviously this quantity sold will be the minimum of xi and di, isn't it? Suppose I stock 20 items and the demand is 50 items during the day. I will be able to sell only what I have, so it will be only xi, right? However, if I have 100 items and the demand is only 20 items, then I will be able to sell only 20 items. So the demand is always, the quantity sold is the minimum of xi and di. And what will be the quantity remaining at the end? This is nothing but R, which is again a function of xi and di, and this quantity will be the maximum of xi minus di comma 0. Because if you have 30 items in stock and the demand is only 10, that means 30 minus 10, 20 items will be basically remaining at the end. On the contrary, if you have 20 items and the demand is 50, more than what you have, then all the items will be sold away, there will be some unsatisfied demand, and you will therefore not be left with any quantity, which is 0. So the payoff from the sale is nothing but the summation of I is equal to 1 to n. That means summation for all the products for I is equal to 1 to n of, this is the revenue that you get by selling the item. So revenue multiplied by the quantity sold, plus this is the Ri dash, which is the disposal value multiplied with the quantity remaining, and this was your cost minus Cixi. Okay. So this is the payoff from the sale Z. Because demands are a random variable, Z is also a random variable, and therefore our consideration is to find out the expression for the expected value of Z, that is Ez, which can be found out by integrating this function over all possible values of the demand. So what we do now is, we say that the expected value of Z is the sum from I is equal to 1 to n. We have this entire expression, integral from 0 to infinity for all possible values of demand. This is the revenue that you earn from sales, this is the revenue that you earn from the disposal of the items, into FD, which is the FIDI, which is the PDF multiplied with DDI. So this is the integral which you have to evaluate here, minus Cixi, which is the cost of the item. Now this integral can be very conveniently split into two ranges. For instance, what we can say is that this very integral can be from 0 to xi and from xi to infinity, right, this very integral. And we can take this particular value here, the revenue from sales can be taken out into di fi di into ddi plus ri xi can be taken outside into integral from xi to infinity fi di ddi. This is nothing but 1 minus the cumulative density function of the demand, right. So this particular expression on the other hand, that is the quantity remaining, this was the first integral, we are talking about the quantity sold, which can be depending upon whether the demand is less than xi or the demand is greater than xi, you have a different function for that. And the quantity remaining is xi minus di, this is the quantity, and this will happen only if the demand is between 0 to xi. If the demand exceeds xi, this quantity will be 0. So in this second case, the integral will, on the second part of the integral will not be there, okay. So if you just rearrange the terms, you get this expression that the sum of all the products from 1 to n, ri minus ci into xi plus ri minus ri prime, integral from 0 to xi di dd fdi ddi minus xi fi xi is basically the expression for the expected value of z. Now what we are interested in doing is from this expression for the expected value of z which we have developed, we are interested in that particular value of z, we are interested in the maximizing the value of the expected value of z. So if you take the partial derivative of the expected value of z with respect to xi, what you would have is this expression ri minus ci minus ri prime into capital F is the cumulative density function of the demand, right, and this is equal to 0. And if we just rearrange the function, our final result comes in a very compact form. This says that fi xi star shows the optimal value, is in fact nothing but this fi xi star will be 0 to xi star fi di ddi, this is the cumulative density function up to the value xi star, is nothing but ri minus ci divided by ri minus ri prime, and there would be one such equation for each product. So I is equal to 1 to n, so you have n such things, and these equations would in fact be pretty simple to evaluate, because what you would have to do is the right hand side is a constant ri minus ci, this is the revenue, this is the cost that you get for the item, this is the revenue, and this is the disposal value. So this is a constant. So particular value of the constant, if you equate it to the CDF of the demand, you know the value, you can find out what the corresponding value of xi star would be from the PDF of the distribution or the CDF of the distribution. Let us take an example to illustrate this approach. Let us see, let us say we have a simple problem of the stochastic product mix in which we have 3 products 1, 2 and 3, and these 3 products have unit cost of 10 rupees, 20 rupees and 30 rupees, and the revenue from sale, if you can sell it during the sale, during the Pragati Maidan sale, then this will cost you 20 rupees, this will earn 20 rupees, 35 rupees and 50 rupees respectively. However, if these are not sold during the sale, then you will probably have to sell them off for a lower value than the cost even, and so these costs are 5 rupees, 10 rupees and 20 rupees. In fact, classically this problem is also known as the newsboy problem, because a newspaper man who has to buy newspapers every day and sell them, the demand for newspapers is also a random variable, and he does not know how many to buy such that at during the whole year his expected profit is maximized. So here we are taking a situation where the news vendor buys the Hindustan Times, the Times of India and India Today, and each one of them is priced differently, each one has a demand which is given here. So this is the case, and what we are saying here is that each product has a range of demands. It has 150 to 250, 0 to 400 and 100 to 300, and for simplicity we assume that all demands are uniformly distributed. They could follow any distribution, so we assume that they are uniformly distributed. So, in order to solve this problem, what we need to do is look at the uniform distribution first. So, a uniform distribution is like this. We are saying that the minimum demand is AI for the ith product and BI is the largest demand for the ith product. So, the PDF of this particular demand is a rectangular function and this particular value will be 1 upon B minus A, because in a valid PDF the total area must be 1, okay. And the CDF for this particular function will be a ramp function going from AI to BI, and at any particular arbitrary value of xi lying between AI and BI, you can from similar triangles develop this particular relationship, because what you can say is at this particular point what is the value of the PDF? It will be this area. So, this area is nothing but 1 upon B minus A into xi minus BA. So, if you then, so this is my cumulative density function fi xi, which is what it is, this area here. So, I can develop a relationship directly for xi equal to AI plus BI minus AI into fi xi, which will be valid for all uniform distributions. Now, you might be wondering as to why I am doing this. You will have to do this because if you want to solve that particular model, then you will need the values of xi corresponding to a given value of the cumulative density function. So, this is an equation which will very easily help us to do that, okay. So, let us try to solve the problem. All that we need to do is we have to calculate f1 x1. What is f1 x1? f1 x1 is nothing but r1 minus c1 divided by r1 minus r1 dash, okay. So, 20 rupees is the cost of this item, is the revenue that you get from this item. So, 20 minus 10, cost is 10 rupees. So, 20 minus 10 in the numerator divided by 20 minus 5, 20 is the revenue and 5 is the disposal value. So, this is just 10 by 15, and x1 by using the equation we have just developed, this equation I am referring to, this very equation, x1 for a given value of xi fi xi can be very easily computed from here, and you have x1 is equal to 150 plus, because this is the minimum value of the range AI, plus 100 is the range of this, into 10 by 15 is the value here. So, you get x1 is equal to 216.67. Similarly, the value for f2 x2 can be easily computed, and this value is 240, and similarly f3 x3, this value is 233.7, corresponding to the values of the CDF value, which is so much. You can easily determine what the values of x1, x2 and x3 are going to be. So, this determines the optimal product mix for the stochastic problem. So, it is a very simple and an elegant solution technique that you have for finding out the quantities of x1, x2 and x3, which will in fact give us the maximum expected profit. Incidentally, how will you compute the maximum expected profit? We had developed the expression for Ez. So, these values of x1, x2 and x3, if you substitute in that expression, you will get the expression for the value of Ez. Another interesting thing that can be computed from here and which is of practical significance is that if you buy 216.67 items and each item costs you 10 rupees, then the total investment in purchasing item A is so much. The total investment in purchasing 240 units of this particular item is 240 multiplied by 20, which is 4,800. And finally, the third thing is if you purchase 233.37 items and your cost is 30 rupees an item, your cost is going to be 7,000 rupees. So, this is like the bill that the vegetable vendor has to pay, and he finds that he is spending the maximum money in product 3 out of his total budget of about 14,000 rupees which he has to spend. Roughly half of it has gone to purchasing the third item. And now So these are very useful insights that you can get into determining the optimal product mix under a situation where the demands are random variables in that case. What we have considered in this particular example is a situation where there are no constraints on the budget, right. For instance, if the person who was to buy these 3 items had more than this much amount of money, he had 15,000 or 20,000 rupees in his pocket, he would not be concerned because he can easily buy all these items and that would be the option. But suppose he had a limited budget of only 10,000 rupees. If he had a budget of only 10,000 rupees, he would have to curtail some of these items so that everything is confined to his budget of 10,000 rupees. So that would be the case of a stochastic product mix with a single budget constraint. We have not addressed that problem will be addressed in the tutorial classes. But what you can see is that ultimately what will happen is that you will have to cut something everywhere, and how much you cut at each of these places is actually determined by the process of optimization. So that problem can be solved by using Lagrangian multipliers superimposed on this particular problem, and we will see how the constraint problem can be solved. Finally, let us look at what we have done today. In today's lecture, we have basically looked at the motivation and considerations behind the product mix problem. We had seen, for instance, as to why product mix is done, because you do not want to put all your eggs in one basket, because there are different kinds of constraints which we enumerated. So you have to be careful about, and you have to be aware of all those things as to why the product mix problem becomes important. And then in this lecture we looked at some commonly used formulations of product mix, illustrating them with examples. We looked, number 1, at the linear programming formulation, which is a classical formulation and is still a very, very useful mode of solving this particular problem. Then we looked at a goal programming formulation for accommodating multiple goals. The major limitation with linear programming is that you can take into consideration only one goal or one objective. So goal programming formulation, which takes a number of deviational variables, can accommodate multiple goals. And finally, we saw a stochastic product mix problem in which there were demands which are following random variable, which demands which are modeled by random variables, and you can have any arbitrary distribution for the demand, and a number of possible applications of this to perishable items in short term sales were actually highlighted, and possible extensions of this model to situations where there are constraints on the budget or the space could in fact be handled by a similar kind of framework with extensions using Lagrangian multipliers. Thank you very much.